Hello student, I am Nirmala Morade, Department of Mathematics from S.V.K.T College, Devali Camp, Nasik. In last lecture we have studied complex conjugate. Suppose we have to given the complex number z equals to x plus iy. Then its complex conjugate is denoted by the symbol z raised to minus z raised to bar or z bar is equals to x minus iy. Also we have studied some results related to the complex conjugate. So the first result is z bar, its bar is same as z, that is the complex conjugate of z bar is same as z, again the same complex number. Mod of z bar is same as z. Next result we have studied, that is related to addition and subtraction. Z plus z2 raised to bar, or that is complex conjugate of z1 plus z2 is same as complex conjugate of z1 plus complex conjugate of z2. Same result for subtraction, same result for multiplication, and same for division. So for division, the denominator, that is z2 number, should be a non-zero complex number. Also we have studied some results. The real part of z can be expressed as z plus z bar upon 2, and the imaginary part is z minus z bar upon 2. And also we have to study some examples using the complex conjugate. We have proved some identity using the complex conjugate of a complex number. This is one of the result, z into z bar equals to mod z square. In today's lecture, we are going to study polar form of a complex number, the exponential form of the complex number, as well as the principal argument and the argument of a complex number. And we will see some examples how to find the given, how to find the argument as well as the principal argument of the complex number, and we write that number in polar as well as in exponential form. Also we will study the parametric equation of a circle using complex number in complex plane. After watching this video, students are able to write complex number in polar form as well as in exponential form. To write the polar or exponential form, we need the principal argument or the argument of a complex number. So after studying this part, students are able to find the principal argument of a complex number, also to write the equation of a circle in parametric form in complex plane. So now let us consider the first concept, how to write the complex number in a polar form. So for that we consider a point xy in xy plane, and let its polar coordinates be r and theta. So we know that the first polar coordinate is nothing but the distance of that point from the origin, and the second polar coordinate, that is theta, is the angle between the segment OP with the positive direction of x-axis. So as shown in the figure, we consider a point P in the xy plane, and the first polar coordinate is r and second polar coordinate is theta. Now also we know the relation between these Cartesian coordinates and the polar coordinates. So we express xy, that is Cartesian coordinate, in terms of r theta, and the relations are x equals to r cos theta and y equals to r sin theta. So first we have to consider here the complex number z equals to x plus iy. So this number is related to the ordered pair xy, and we consider here r and theta are the polar coordinates So these are the relation between polar and Cartesian coordinate, that is we express xy in terms of r and theta. Also we know that theta and r, both numbers, both polar coordinates can be written in terms of x and y. So here theta can be expressed as tan inverse of y upon x by just taking the ratio of this y upon x and then take tan inverse of both sides. So we get here tan theta equals to y upon x, or simply theta equals to tan inverse of y upon x. Also squaring and adding these two equations, we will get here r square equals to x square plus y square. So r equals to root of x square plus y square. So now if you put x equals to r cos theta and y equals to r sin theta in z, z is a complex number here, x plus iy. So we get here z equals to r cos theta plus I times r sin theta, take r common, so z can be written as z equals to r times cos theta plus I sin theta. So this form is called as the polar form of the complex number. That is, we express the complex number in terms of its polar coordinates, that is in terms of r and theta. So our next topic is how to express the complex number in exponential form. So one more thing is here, here theta should be non-zero. Suppose we consider the given complex number in polar form. So for that z should be a non-zero number. So because for z equals to 0, the number theta is not defined here, or which is undefined. So always remember, if we express the z in terms of the polar form, z should be a non-zero complex number. Okay, before studying the exponential form, let us consider how to find the argument of a complex number, or what is the argument of the complex number. So now here r is denoted by the symbol mod z, that is the modulus of the complex number. It is nothing but the length of the radius vector for z, length of the radius vector for z, and the theta, which is measured in radian, is the angle between the radius vector z and the positive real axis. So this theta has infinite number of values, including negative ones, and that values differ by integral multiple of 2 pi. So these quantities are involved in polar form as well as in exponential form of a complex number. So remember here r is the length of the radius vector z, and second theta is always measured in radian, and it is the angle between the radius vector z and the positive real axis, and this theta has infinitely many values including negative ones, and they differ by integral multiple of 2 pi. So we have to calculate these different values of theta by using the equation tan theta equals to y upon x. Here this value of theta is called as the argument of the complex number, and it is denoted by the symbol a, small a, r, g, z. So remember here the argument of the theta, each value of theta, actually here theta has infinitely many values, and each value of the theta is called the argument of z, and it is denoted by the small letters a, r, g, z. So see in the diagram, this is a complex plane. Here x axis is nothing but the real axis and y axis is the imaginary axis. Here the radius vector is z, which is the point z represent the complex number, its tip represent the complex number z equals to x plus iy, and the length of the radius vector is r, as see in the figure. And now see here theta. If you see the angle between the real axis, that is x axis, and the vector z is theta, but if we complete one circle again, then we get infinite many values. Okay. Okay, our next part is the principal argument of the complex number. So we know that each value of theta is called the argument of the z, and there are such a infinite many angles or values are there. So among this value we select the unique value which is denoted by capital theta. This is the symbol for the capital theta, and this capital theta is called the principal value of z, principal value of theta, which is denoted by the symbol capital A R G Z, and this value of theta is satisfy this inequality. Minus pi is strictly less than theta, capital theta is less than equal pi. So the value of theta which satisfy this inequality, minus pi is strictly less than theta is less than equal pi, is called, this unique value is called the principal argument of theta, and it is denoted by the symbol capital A small r g z. Now it is obvious to see the relation between these two values, principal argument and argument of the complex number. So this is a relation between the argument and the principal value of the theta. So argument of z is equals to the principal value of theta plus 2 times 2n pi. Here n is the integer, that is n is equals to 0, plus minus 1, plus minus 2, and so on. So here you can easily observe that the relation between argument of z and the principal argument of z by using this diagram. So our next topic is exponential form of the complex number. So to write the complex number in exponential form, we will use the Euler's formula. So Euler's formula says that e raised to I theta, that can be written as exp I theta, is same as cos theta plus I times sin theta. So to write the number in exponential form, we use this formula. So as we know that the polar form is z equals to r in bracket cos theta plus I sin theta. So the second bracket cos theta plus I sin theta is replaced by e raised to I theta. So we will get this form of the complex number, z equals to r times e raised to I theta, and this form is called the exponential form of the complex number. So now here to write the exponential as well as the polar form of the complex number, we required r and theta, that is the length of the vector, radius vector, and the argument of the complex number. So now let us consider first example. So now in example we will study different types of examples. Observe these examples, all these examples are different, so observe it carefully. So these examples will helpful to you to find the argument as well as the principal argument of each and every complex number. So now let us start with the simplest example. The first example, we consider a complex number which is purely real. That is, definitely it lies on real axis. Okay, so I consider first it lies on positive real axis. So take z equals to 3. So this 3 can be written as 3 plus I times 0. So its real part, that is x is 3 and y is 0 here. So first we concentrate on principal argument. Principal argument is the argument of the complex number such that minus pi is less than theta is less than equal pi. So it lies between minus 180 to plus 180, and it is not equals to minus 180 but equals to plus 180. And it is an angle between the radius vector and the positive real axis. So now here this radius vector lies on the real axis. So the angle between the radius vector and the real axis is 0. And that is why this is a principal argument of z, which is 0, because 0 satisfies the condition minus pi is strictly less than theta is less than equal plus pi. So this is the principal argument. So every real number whose radius vector lies on positive real axis has a argument, principal argument 0. So we know the relation between the principal argument and the argument of the number. So argument of z is same as principal argument of z plus 2 n pi, where n is a integer here. So now just putting principal argument in this equation. So we will get here the argument of the complex number. So let us see, this is the argument of the complex number, argument of z equals to 2 n pi. Okay. So let us continue with the second example. I suggest here observe each and every equation, every example carefully here. So this is second example. We consider a complex number on positive y-axis, that is positive imaginary axis. So let us consider the number z equals to I2. So this can be written as 0 plus I times 2. So now if you consider this radius vector lies along positive imaginary axis, that is y-axis. So angle between the radius vector and the positive real axis is obviously here 90 degree. So the principal argument is 90 degree here because it lies between minus 180 to plus 180. So this is our principal argument. Then argument of z is principal argument plus 2 n pi. So the argument of z is pi by 2 plus 2 n times pi, where n is the integer here. So consider the third example. Third example, we consider z as a minus 4. So minus 4 lies on z equals to minus 4 lies on negative x-axis. So the principal argument is obviously here the angle between positive x-axis and the negative x-axis is 180 degree. So argument, principal argument is z equals to pi, and so again write the argument of z by adding 2 pi n in the principal argument. So see here, the argument of z is equals to pi plus 2 n pi, where n is any integer. So let us continue with the fourth example. Obviously in fourth example we consider a complex number on negative y-axis, that is negative imaginary axis. So I consider here example as z equals to minus 5i or I times 5. It is a purely imaginary number. So now here the principal argument of the complex number is minus pi by 2. So here we consider the argument of the complex number is the angle between the negative angle between the radius vector and the positive real axis or the real axis, positive real axis. If you measure or count the angle in clockwise direction, then you can treat this angle as a negative, and opposite, if you count opposite to or counterclockwise direction, we consider it as a positive. Now see here in the diagram, the angle between the z-axis and the positive x-axis, that is the positive real axis, is pi by 2. Since we have to count this angle in clockwise direction, that's why we have to write minus pi by 2. So the here principal argument is minus pi by 2 because it lies between minus pi and plus pi. And then write the argument of z by adding 2 n pi in the principal argument, where n is a integer here. Okay, now let us consider more 4 examples. So by taking each complex number in each quadrant, see what happens. So first simplest complex number is 1 plus I, which is in first quadrant. Here x is 1, y is 1. So the complex number lies in first quadrant. So to find the argument, we use the formula here, tan theta equals to y upon x. So here y is 1, x is also equals to 1. So put x and y both are equals to 1, so we get here 1 upon 1 equals to 1. Since the point lies in the first quadrant, so here theta equals to pi by 4, that is 45 degree, but we know that we measured the theta in radian and that's why we write here pi by 4. Okay, see in the diagram also. So the argument of z is pi by 4 plus 2n times pi, where n is any integer, that is 0 plus minus 1 plus minus 2 and so on, and just put here the principal argument. So we will get here argument of z equals to pi by 4 plus 2 times 2n pi. Okay. So let us consider the second example. So we consider here z equals to 1 minus I. The corresponding point is 1 minus 1. So this point we know that lies in the fourth quadrant. So if you measure the angle between radius vector and if you observe carefully, if you find the angle between two lines or two vectors, so there are always two angles, one is acute and one is the obtuse. We consider here the acute angle. So see in the diagram, if you measure the angle from positive real axis to radius vector, it is 315 degree. Okay, but it is not a principal argument. To find the principal argument, now we find the angle between the z axis, angle between the radius vector and the positive real axis or real axis in clockwise direction. So first I have to find here tan theta, put y equals to minus 1, x equals to 1 here. So we get minus 1 upon 1 is minus 1 here. So theta is minus pi by 4. Theta is minus pi by 4. Okay. That is we count this angle in clockwise direction from real axis to z, radius vector z, and that's why I have to written here minus pi by 4. Okay. So the argument of z is obtained by just adding 2n pi in principal argument. So this is our result. So that is obvious one. So now if the point is either in first or the fourth quadrant, it is easy to find the principal argument. So now next example, suppose consider the point is in third quadrant. So I have to first put the diagram here. So consider z equals to minus 1 plus I. Z equals to minus 1 plus I. So corresponding point is minus 1, 1, which is in the second quadrant. Okay, it is easy to draw the points. See in the diagram, the point radius vector lies in the second quadrant. So now find the tan theta. Tan theta equals to y upon x, just put the value. So we get here tan theta equals to 1 upon minus 1 minus 1. So directly we can write here theta is minus pi by 4, but that is wrong because the point is in second quadrant. So how it is possible theta equals to minus pi by 4? So actually see in the diagram, this theta is minus pi by 4 is the angle between radius vector, is the angle between the radius vector and the x-axis, and we count this angle in negative real axis, and we count this angle in clockwise direction. That's why we will get here theta equals to minus pi by 4. If we subtract, now see in the diagram, the angle between positive real axis to negative real axis is total pi, and we subtract that portion, and that's why here the angle is pi minus pi by 4. So the output is here 3 pi by 4. So this is our principal argument because it lies between minus pi to plus pi. So using regular formula, write the argument of z by just adding 2 pi n. So okay, that is easy for us. So let us consider the next example. If point lies in the third quadrant, then how to find the principal argument? So consider point is minus 1 minus I. So corresponding point is minus 1 minus 1. This point is in third quadrant. So now here again we can find the tan theta, which is y upon x. So put y is minus 1, x is minus 1, so output is plus 1 here. So if we directly write the angle, so the answer is pi by 4 directly. But if the point is in third quadrant, how it is possible the angle between the positive real axis and the z radius vector is pi by 4? So actually see in the diagram, it is the angle between the negative real axis and the radius vector is pi by 4. Okay. But we require this angle, since this angle is pi by 4, angle between negative real axis and the radius vector is pi by 4, and we required actually angle between the positive real axis and the z coordinate. Okay. So in this case we consider the whole angle, that is angle between negative to positive real axis is pi, and if we subtract that angle, so we will get the required answer, which is 3 pi by 4. But we count the angle in clockwise direction, and that is why we put the minus sign there. So the argument of z in this case is minus 3 pi by 4. Okay. So here the argument of z, find the argument of z by using regular formula. Okay. So if you are able to find the principal argument or argument of z, you can easily write either the number is in complex form, is in polar form, or the exponential form. So let us consider some examples. So we write the complex number either in exponential form as well as in the polar form also. So now for that consider the first example, z equals to minus 1 minus I is equals to x plus iy. So here x is equals to minus 1, y is also minus 1. So first we have to find r. The formula for r is square root of x square plus y square. Just put the values. The calculations are very easy. So we get here r is equals to root 2. So we know that the polar formula is z equals to r times cos theta plus I sin theta. Put the value of r, which is root 2, and next part is theta. Already we have to find that theta, just put the value of theta. So we get here the polar form of the complex number. See here in last lecture, example, already we have to find theta equals to minus 3 pi by 4 for the value of for z equals to minus 1 minus I. So this is a polar form of the complex number. So now to find it, to write this number in exponential form, we use the formula z equals to r times e raised to I theta. Okay, this is another one. Either you can use to write the polar form or the exponential form, you can use either principal argument or the argument of the complex number, that does not matter. So you can observe here the second form, or in second form I use here the argument of the complex number, and if I put n is equals to 0, I will get the first form here. So the first form is one of the polar form of the complex number. Okay, so we write the exponential form of the same complex number r equals to e raised to I theta, that is r times exp I theta. So put here r equals to root 2 and theta is minus, either minus 3 pi by 4, or put the principal argument, or you can put the argument of the complex number also. Okay, next part is let us say how to write the equation of a circle in complex plane by using parametric form. So now for that we consider the complex number in exponential form. So z is equals to r times e raised to I theta. If we put r equals to 1 here, so z becomes e raised to I theta. If we calculate its mod, So mod of e raised to I theta, that is mod of cos theta plus I sin theta, which is same as root of cos square theta plus sin square theta, so which is 1 here. And if you put r equals to 1, so you can easily observe that the distance of all the complex number from the origin is equals to 1, that is all these complex numbers lie on the circle with center 0, 0 and radius 1. So remember, the complex number z equals to e raised to I theta lie on the unit circle with center as a origin. So now using this one, you can easily find the value of e raised to I pi. So e raised to I pi means here the argument is pi, means here all these complex number e raised to I pi lies on negative real axis, so its value is -1. E raised to minus I pi by 2, here angle theta is minus pi by 2, so it lies on negative y axis, that is negative imaginary axis, so its value is -I. And next one is the e raised to minus I pi, which is also 1, because if you consider theta is minus pi by 2, so if you consider the angle pi by 2 4 pi, and if we do 2 rotations, we will be reach at positive x axis, so its value is equals to 1 here. So let us consider next part is the parametric equation of the circle. So consider z equals to capital I e raised to I theta. So take the mod of both sides here. So mod of r, mod of capital R into e raised to I theta is mod of r is positive here, and mod of e raised to I theta is 1 here, so mod z equals to r. So we can say here z equals to e raised to I theta, where theta lies between 0 to 2 pi, theta is from 0 to 2 pi, represent a circle with radius r and the origin 0. So this is a parametric equation, z equals to capital R e raised to I theta, where 0 is less than equal, theta is less than equal 2 pi, represent a circle with center 0, 0 and radius r. It is called the parametric equation of this circle. So let us generalize this concept. So for that we consider a circle with center z0 and radius r. Actually, even if you put value of z as x plus iy and z0 as x0 plus iy0, if you put all these things solid, so definitely you will get a circle with equation x minus x0 bracket square plus y minus y0 bracket square equals to capital R. So this equation mod of z minus z0 equals to r represent a circle with center z0 and radius r. So we write this equation in parametric form. So the parametric form of this equation is z equals to z0 plus capital R times e raised to I theta. Theta varies from 0 to 2 pi. So this is a parametric equation of the above circle. So this is a diagram. So this is some assignment for you. So watch the video carefully and do this assignment. Definitely all the examples in this video are useful for you to solve the assignment of the topic. So this is additional reference for you. Complex variable and application by James Brown and Churchill. This topic is covered in chapter 1. Also additional exercise is also given, so try to solve the additional exercise also. Let us summarize today's lecture. In today's lecture we have studied polar form of the complex number. If z is a complex number, then it can be written as z equals to r times cos theta plus I times sin theta, where r is equals to root of x square plus y square and theta is tan inverse of y upon x, or tan theta is y upon x. Also we have to study the exponential form. So if you know r and theta, then z can be written as r times e raised to I theta or r times exp r theta. So here we can consider the argument or principal argument also. So also we have to study how to find the argument and principal argument of the complex number. So the principal argument of the complex number is one of the value of argument which is denoted by capital theta, and it satisfies the inequality minus pi is strictly less than capital theta is strictly less than equal pi. Then this value of the argument is called the principal value of the argument, and it is the unique value. And relation between the argument and principal argument is the argument of z is equals to the principal argument of z plus 2n pi, where n is a integer here. Also we have to study some examples, so do the practice of all the examples, and we have to study the last part as a how to write the equation of a circle in the form of complex number. So mod z equals to r represent a complex number, mod z equals to r represent a circle in complex plane with center as a origin and radius r. Its parametric equation is z equals to r e raised to I theta, where theta is lies between 0 to 2 pi. In next lecture we will study the product as well as the powers of a complex number using the exponential form and some examples related to it.